In last class, we have discussed about the zero order reaction. Here now we are going to discussing about the first order reactions. So first order reaction is nothing but the order of reaction is 1. According to the rate law, the order of the reaction is 1. Here we have given few examples for the first order reaction which is determined experimentally. Right. So first one is decomposition of hydrogen peroxide. Decomposition of hydrogen peroxide in aqueous solution. Similarly, hydrolysis of methyl acetate in presence of acidic medium. If you observe here the reactants here we have one is methyl acetate undergo, another one is hydrolysis. That means water we have added. So whenever the excess of amount of water is added, that amount can be ignored in the calculation of order of the reaction, right? As we have discussed in the last class, we have discussed one numerical also based on that. If you take an excess concentration, that you should have to neglect in the calculation of the order of reaction, right? So therefore here if you observe according to the reactants number of reactants are 2, but here the order of the reaction is 1, and hence this reaction is also called pseudo order reaction. Clear? So now here once again I'm repeating, the order is determined experimentally but not by seeing the number of moles of reactants added in the reaction mixture. Clear? Now another one is inversion of cane sugar is also an example of first order reaction. Similarly, decomposition of ammonium nitrite into N2 and water. And last but not least, this is also a first order reaction, that is hydrolysis of diazo derivatives. Benzene diazonium chloride undergo hydrolysis will give phenol and nitrogen gas. Clear? So in the case of gases, here it is very important note, you need to observe that you have to consider the pressure in the place of concentration for the gaseous reactions. Clear? Now let's see the integrated rate constant, integrated rate constant, integrated rate constant, integrated rate constant for first order reaction, for first order reaction. Clear? So as the story, you know that the same story every time I will explain, that will be the reaction. Initial concentration I have taken a mole per liter, right? A mole per liter, and initially there is no product, right? After some time some x mole per liter is obtained, right? And the remaining concentration of the A will be A minus x mole per liter. Clear? Now let's see about the rate of that first order reaction. So I am writing the rate of that first order reaction R equal to K into A to the power of 1, right? Whereas R is nothing but rate of reaction, change in concentration by change in time. So as already I told you, integrated, that means the rate is calculated at a small interval of time. So therefore dx by dt is equal to K into A to the power of 1. So here dx by dt equal to K into what about A? A is the concentration of reactant after some time. That means A minus X. As per the data, we are taking the concentration of reactant as A minus X. Clear? As A minus X. I will write neatly A minus X. Clear? Now here I am writing the same variables at same side. That means x variables I am separating, right? Dx by a minus x equal to k dt. Clear? Now dx by a minus x equal to k dt. Now I am doing both side integration in order to get our small interval rate constant. At small intervals rate constant we have to calculate. So therefore integration of dx by a minus x equal to integration of k into dt, right? That means integration of 1 by a minus x, we know that, right? That is minus ln a minus x. Here x is the variable which is getting changed, right? So therefore it will be the minus. So therefore minus ln a minus x, clear, is equal to, obviously we know that k is the constant, there is no change even though you integrated. Okay, now integration of dt, that will become t, and mathematically after doing the integration we will get a constant that is denoted by c, and overall this expression I am assuming as equation 1, clear. So minus ln a minus x equal to kt plus c. So this is what we have calculated at a particular time, right? At a particular time, you can observe here we have taken the concentration of a is a minus x. Now what will happen if we take at initial time, that means at a zero time, starting stage, at a zero time, obviously there is no product, that means x equal to also 0. Therefore, at t equal to 0 and x equal to 0. So I am substituting this data in equation 1. Equation 1, in equation we are 1 we are substituting in order to get the initial stage. What will be the rate constant at initial stage? Clear. So therefore minus ln a minus 0, because I have substituted x equal to 0 here, right, is equal to k into, at a time will be the 0, right, at a time will be the 0, then we will get the constant, right. So therefore here minus ln a equal to c, so we have got integrated constant value, that is minus ln a, this is I am assuming as equation 2, clear. Now you can substitute this value in equation 1 in order to get the complete k value. So therefore k equal to, I will write this as, by substituting in that, okay now. So minus ln a minus x is equal to kt minus ln a, clear, kt minus ln a, clear. Now upon simplifying we can get kt equal to, right, kt equal to ln a minus ln a minus x, clear. So I'm taking this minus ln a here and it will become plus ln a, so therefore ln a minus ln a minus x. Now kt equal to, we can write it is as ln a by a minus x. We know that ln a minus ln b is equal to ln a by b, clear. Now k equal to 1 by t ln a by a minus x. This will be the rate constant for first order integrated equation, clear. Now upon this natural logarithm base e, we can convert into the logarithm 10 base 10 by multiplying with 2.303. Therefore we will get a k equal to 2.303 by t log a by a minus x. So this will be the rate constant for the first order reaction, clear. So now here where a is initial concentration, we know that already, where a is initial concentration, right, of reactant, initial concentration of reactant, and where a minus x is the concentration of reactant, concentration of reactant after some time, after some time, clear. So here the rate constant for first order reaction will be, once again I am repeating, k equal to 2.303 by t log a by a minus x, clear. Now let's see the continuation part, the same derivation as per NCRT we can observe here, as per NCRT you can observe here the integrated rate equation for first order. So similarly in my session, in my class, I have assumed as A is gives rise to B, right? As per NCRT, A is the reactant, obviously, or reactant generally denoted by R. So reactant is gives rise to product, clear? So here I have assumed the reactant as A, generally has taken the reactant as directly as R denoted by R. So reactant is gives rise to product, and obviously rate of the reaction with respect to reactant he has taken, that is minus dr by dt is equal to, right, k into r. Clear? Minus dr by dt with respect to reactant rate of reaction will be, right, is equal to, rate law we are writing k into concentration of reactant to the power of 1, right? So now here minus dr by dt is equal to k into r, right? Or you may write, this one as dr by concentration of r. That means writing the same variables at same side. I have explained in terms of x, right? Now he has taken in terms of r, so that's why here we are taking the same variables at same side. That means here I am writing minus dr by r equal to kdt, right? Or you may take this negative symbol here, so you will get dr by r equal to minus kdt. Is it clear? Right. Now upon integrating this equation, we know that upon integration what will happen, right? So ln r is equal to minus k, obviously is the constant, t, d integration of dt will become t, and integration constant in my derivation part I have indicated with c. Here they have given with I letter. Clear? So upon integrating, we have got an equation which is indicated as equation 1. You can observe here. So ln r is equal to, right, ln r equal to minus kt plus I. Clear? Minus kt plus I. Now here this is I have assumed as equation 1. When time equal to 0, then the concentration of reactant is initial concentration, right, 0. So at that time r will become r0. They have indicated r as r0 at time 0, right? So here they have given r0 is the initial concentration, where r is the concentration after some time. Clear? Right. Now here upon substituting this data, we have got here I value. In our derivation part we have got c, right? There is ln a, because a is I have assumed as initial concentration. Here r naught is the initial concentration, so I equal to, we have got ln r naught. Clear? You can write r naught like this. So now this I value I'm substituting here, so therefore I have got ln r is equal to minus kt plus ln r naught. Clear? Now upon simplifying we will get the expression as minus kt equal to ln r by r naught. Clear? Ln r by r naught. Clear? Now k equal to, we will get 1 by t ln r naught by r. You can observe here the expression, right? So here you can write minus k equal to 1 by t ln r by r naught. Okay na? So here minus, if I am taking here, so k equal to 1 by t ln r naught by r. Clear everyone? So here in our derivation part I have got k equal to 1 by t ln a by a minus x, where here initial concentration denoted by r naught I have indicated with a, right? So here remaining concentration indicated as r I have indicated with a minus x. That is the only difference. You can approach that derivation part or this derivation part, both will be the same. So based on the variables we have to solve the questions. Clear? So now here according to the different intervals of time, so we have taken at a t1 time the concentration become r1, so I have given one more equation. Similarly here at time 2 interval, r2 will become like this. So ln r2 equal to kt2 as per this previous our expression. Clear? Now based on this we are subtracting ln r1 by ln r2, right? Ln r1 minus ln r2 equal to, we have got kt1 minus of minus kt2. Clear? kt1 of minus kt2. So upon that simplifying ln a minus ln b, right? Here k into t2 minus t1, then k equal to 1 by t2 minus t1. ln r1 by r2. This one will be at different times of intervals. Clear? Now we can also draw the graphs. Here you can observe one question. You can observe here one question. The most important point you have to notice here. If we plot a graph between ln r naught log r naught by r versus t, what will be the graph and what will be the slope? Clear? So we know the first order rate equation as k equal to 2.303 by t log r naught by r. So here log r naught by r they have taken on y-axis, right? And here time is taken on x-axis. So from this I am separating log r naught by r, so we will get kt by 2.303. Clear? So log r naught by r equal to kt by 2.303, right? So this is I am assuming as y, right? This is assuming as, that means t is taken as an x-axis. So therefore the reaction, the graph is comparing with the y equal to mx, then the slope will be m, that will be the k by 2.303. Clear? So what will be the slope if they ask when the graph drawn between log r naught by r versus t, the slope will be positive slope. Clear? So m equal to k by 2.303. We can also observe here one more first order reaction. They have given that, right? That is hydrogenation of ethene C2H4. C2H4 gives ethane. This is also indicates the first order reaction. And one more important point, all first order reactions are mostly all natural and artificial radioactive decay. All natural and artificial radio decay of unstable nuclei takes place by first order kinetics. That means all radioactive decay considered as first order reactions. Clear? Example, you may observe that here radium. Radium is the radioactive element, right? We know that radium is the radioactive element, right? Radioactive element. It undergo natural decay into helium and radon. Clear? So this is also considered as first order reaction. Clear? Now here few more graphs also given in the NCERT. What would be the graph? What would be the slope if we draw a graph between ln r versus t, ln r versus t, and log r naught by r versus time. Clear? So just now we have seen the log r naught by r versus time. Slope will be the k by 2.303. And if you draw between ln r versus t, the slope will be negative with an intercept. Clear? So these will be the very important graphs you need to learn. Clear? What would be the graph or what would be the slope, they will ask. Clear? Now next we can also observe about the, we can also discuss here one numerical will be there, right? Initial concentration of N2O5 they have given. Initial concentration of N2O5, you can observe here initial concentration of N2O5, right, for the following first order reaction is 1.24 into 10 power minus 2. This is what initial concentration. Clear? Now at a 318 kelvins, now the concentration of N2O5 after 60 minutes they have given 0.202 into 10 power. That means at two different intervals of time, right? One will be the initial time, that means time equal to 0. Then another one is after 60 minutes, that means time equal to 60 minutes. They have noticed some change in the concentration, and based on that we have to calculate the rate constant at the same time. Clear? So we know that formula, right? That will be the k equal to, I will write here the formula at different intervals of time. Obviously time equal to 0 initial time, that will be t1 equal to 0, right? You may write directly as also k equal to 2.303 by t log a by a minus x in our version. Clear? Or else you can take r1 by r2. Clear? So k equal to 2.303, time obviously 60 minutes, right? Obviously initial time 0 minutes, right? So 60 minutes. So 2.303 by 60 into log A means initial concentration they have given as 1.24 into 10 power minus 2 divided by A minus X. That means after 60 minutes, what about the concentration of reactant at after 60 minutes? After some time, you know my concept, right? After sometime the remaining concentration will be A minus X, right? So that means A minus X here they have given as 0.20 into 10 power minus 2. So now you can simplificate, you will get the rate constant. Clear? Simplificate, you will get the rate constant as k equal to 0.304 minutes. Clear? Now let's see the most important case in the first order reaction. The most important case in the first order reaction, that is first order reaction in gaseous phase. This is what very important in a gaseous phase. Already I have explained in basics, when the reactants are taken gases, you need to consider pressure instead of concentration. Clear? So at that time, if all are the gases, reactants as well as products, suppose let us imagine here a reaction A converted into B and C and all are gases. So at that time, what will be the rate constant in terms of pressure for this reaction? Clear? Now let's check what will be the rate constant, right? So directly I have written the equation as A is gives rise to B plus C, right? A is gives rise to B plus C. I have taken at a time 0, at initial time I have assumed that P1 is sorry, this one will be the Pi as per here. Pi is the initial pressure in atmospheres, whereas in terms of concentration I have assumed as A, small a I have assumed, right? So here in terms of pressure, initial pressure here we have to assume as Pi. Obviously initially there is no products, there are no products, right? So after some time, at a time, whatever the time, 5 minutes, 10 minutes, 20 minutes, 1 hour, 2 hour, whatever, after some time something is obtained, that is I am assuming as X atmospheres, X atmosphere. And what about the remaining concentration, sorry, remaining pressure of the reactant, remaining pressure of the reactant, that will be the Pi minus X, Pi minus X. Clear? Till here it is clear. Initial pressure and after some time the pressure of the reactant, after some time the pressure of the reactant will be the Pi minus X. Clear? Now I am calculating the total pressure after some time. Total pressure after some time I want to calculate total pressure after some time. That means total, that means Pi minus X, right? X and X. So total I have got Pi plus X, right? Even I will write once again here, Pi minus X plus X plus X. This is what this would be the total pressure after some time, right? So plus X minus X is get cancelled, we have got Pi plus X. Clear? So this is what a total pressure Pt equal to Pi plus X after some time. So from this I would like to calculate what will be the product pressure. That means what would be the X value? X will be the amount of pressure, sorry, the pressure is obtained, the pressure is obtained after some time. That means X I would like to calculate. Therefore X is equal to Pt minus Pi. Please note down here, this is very important. So X we can calculate by the total pressure minus initial pressure. Clear? Now what I am doing here, I am taking the basic mathematical expression for the first order reaction. K equal to 2.303 by T log initial pressure divided by, as per the formula, we know that our formula log A by A minus X. Whereas concentration ki place we have to write pressure. So therefore initial concentration A, here initial pressure I am assuming Pi, right? And A minus X, what about A minus X? A minus X is the remaining concentration of the reactant over there when it comes to concentration. Then what about here? Instead of ai instead of a minus x, we have to take pi minus x. That means that is the pressure of a. That means that is the pressure of a. Clear? Now let's expand this mathematical expression. So therefore k equal to 2.303 by t. Pi means initial pressure. And what about PA? Pressure of A. We know that pressure of A is remaining concentration. That means Pi minus X. Right? So now we know that X value, you can observe here X value. So you can substitute that A will be Pt minus Pi. Right? Therefore, Pi minus Pt plus Pi. That means 2Pi minus Pt. So therefore, the gaseous phase first order rate constant will be the 2.303 by T log Pi by 2Pi minus Pt. Clear? Right. Now let's continue about the T half of first order reaction. T half of first order reaction. Right. Now we are going to calculating the T half time or half life of the first order reaction. So once again I'm writing for first order reaction, right? So initial concentration, we know that what we will assume, initial concentration will be the A mole per liter. Clear? Now what will be the product? 0 mole per liter. Now in order to calculate T half, that means time taken for the completion of the half of the reactant. Time taken, the time taken, this is what time equal to 0. Initially A is there. Now to become half of that initial concentration, whatever the time is required, that time will known as half time, half life of the reaction. That means small a will become a by 2. Whatever the time is required, that will be the T half. So now as per our concept, whatever the amount is obtained, that may be half time or particular time, whatever, that I will assume as x, right? So therefore here x equal to a by 2. I am assuming that something is obtained, a by 2 or a by 3, whatever. But here we are discussing a by 2 for half life. So this a by 2, mathematically I am assuming something is obtained as x. Therefore x equal to a by 2. So therefore, in order to calculate first order T half from this expression, we have to substitute x equal to a by 2. At that time, x equal to a by 2, whatever the x equal to a by 2, whatever the time is required for that process, that time will become T half. So therefore, k equal to 2.303 by T half log a by a minus a by 2. Is there any doubt? Is there any doubt? Where x has a by 2, at that time will become t half. So I have substituted that data and simplifying k equal to 2.303 by t half log. You can simplify this one as 2a, right? 2a minus a by 2, that will become a by 2. So therefore log a by 2. That means k equal to 2.303 by t half log 2. That means a by 1 into 2 by a. Clear? Simplification you can observe here. So we will get only, so therefore T half equal to 2.303 by k log 2. Log 2 value we know that is 0.3010. Therefore, upon simplifying, we will get a 0.693 by k. This will be the first order half life. This will be the first order half life is 0.693 by k. That means half life is independent is independent on initial concentration, but it is inversely proportional to K. Right, so very important point here. T half is independent, it does not depends on the initial concentration. So if we plot a graph between T half versus A, this will be the graph. Clear? So if you plot a graph between T half versus K, that obviously inversely proportional, right? You will get like this. Clear, everyone? So T half is equal to 0.693 by K. Clear? So that will be the half life of the first order reaction. Clear? Now you can see here few more examples, few more numericals based on the half life of the first order reaction. So they have given a first order reaction K equal to 5.5 into 10 power minus 14. They have given second inverse, right? First order. Then they are asking about T half. Just now we have derived a formula. T half is equal to 0.693 by K. Now you can substitute here 0.693 by K and simplify, you will get the answer. Clear? And similarly they are asking one more question, that show that in a first order reaction the time required for the completion of 99.9 is 10 times of T half. Right, so what he is asking, show that time taken for 99.9% is equal to almost 10 times of T half. So this is what we have to prove. Clear? So let's will prove time taken for 99.9% is equal to 10 times of T half for first order reaction. He is asking that first order reaction. So now first order reaction T half, first order reaction T half, we know that is T half equal to 0.693 by K. Clear? So therefore I am writing once again the first order rate constant also, that is K equal to 2.303 by T log A by A minus X. Clear, everyone? Now here K equal to I am writing as 0.693 by T half. Shall we write from this mathematical expression? Right. So I am changing this here and here. So instead of K, I am writing 0.693 by T half is equal to 2.303 by T. This T we have to take in as 99.9%. Clear? Log A by A minus X. We need to observe the relation in between these two. Clear? Now I'm taking the relation between these two as like this. I'm changing the variables. T 99.9 divided by T half is equal to 2.303 divided by 0.693 log A. Log A. Here A, I'm assuming 100% will be there. Whatever the amount is there, 100%. Clear? A, I'm assuming as initial concentration is 100. Clear? Initial concentration is 100. Clear? And he is asking the amount 99.9 is completed. The amount 99.9 is completed amount. That means X. X is completed 99.9. Right? For that, he is asking the relation between half-life versus time taken for 99.9 completion. So therefore I am substituting 100 minus 99.9. Clear? So now here T 99.9 by T half is equal to 2.303 divided by 0.693 log 100 by, now here log 100 divided by 100 minus 99.9 will be 0.1. Now upon this simplifying we will get 1000, right? So therefore this I will write it as log 10 power 3. That means log 10 power 3 is nothing but 3 log 10. We know that log 10 will be the 1. So remaining I am writing as it is T99.9 by T half equal to 2.303 divided by 0.693 into 3. Clear? So you can observe here rough calculation I have done. Clear? So therefore here upon this multiplying T99.9 divided by T half is equal to 3 3 is 9, 0, 3 3 is 9, 3 2 is 6, right, 0.693. So upon these two simplificating, you will get roughly 9.9 something. So I am taking as approximately 10. So therefore, time taken for 99.9 by T half is equal to 10. So therefore, time taken for 99.9 is equal to 10 times of T half. Very, very, very important. Clear? So learn the relation. Like that, if you are having time, you can also prove that. I will give you one more question. Time taken for 75% is equal to 2 times of T half. This is also one relation between the 75% completion, whatever the time is taken, that will be the half, 2 times of half life of the first order reaction. Okay now. So if you are having time, you can also prove like in the similar way. Clear?